guess you'll tell me in 10 minutes. All right. So, I know people see me get up and grab the microphone and there's a few going, oh no, what's he going to say? Well, you'll be finding out shortly. But we're actually, we've been working on this for a little while. You know how sometimes when you come to a conference and sometimes consultants can go on a little bit. No, Sarah, you're really good. Don't take that way. But sometimes we can, and it's like they can talk from not experience sometimes, a bit theoretical. Well, today, what we've been able to do is to actually organise Brendan from Kembla. Now, some of you may not know what Kembla is all about, aside from being down in Port Kembla, which is a great place if you go surfing. But Kembla is actually responsible for, can I say, almost the majority of copper pipes and stuff like that go into healthcare. So everybody's hospital that's here will probably have that copper in your facility. And so I thought, who best to talk about copper corrosion than the people that actually make copper pipe? Sound pretty logical, right? So I'd like you to welcome Brendan. He's going to talk for about 10 minutes, and then you'll have to endure me after that. All right, so can you welcome Brendan, please?
All right, thanks very much, Mark, and very much appreciate the opportunity to talk on behalf of Kembla today with you all. So I've just got up a list up here, and velocity and installation. So when we talk about erosion, corrosion, it's pretty much on the lips of everyone at the moment around what's happening, not only in hospitals, but in commercial buildings as well. And so a long list of things that can contribute to erosion, corrosion. Velocity and installation get the most limelight, and they are very, very important things, and they do have a major impact. But two things that escape everyone's lips, and what's something starting to become quite evident in what we're looking at, but it is also very hard to quantify, is entrained air and dissolved gases. All right, so dissolved gases and entrained air. So it's very important to know that there is a difference between the two. Entrained air within a piping system is where air and water are in separate phases and from one another. Typically forms large, small bubbles within the piping system, whereas dissolved gases in water is a contribution to cavitation. So instead of bubbles forming as a gas, it's amongst the water, and it occurs when the dissolved gases sit in between the molecules of water. So that's the difference. So how does air actually get into the system? So it's naturally occurring as part of the mains water. It's commonly quoted that it's around 2%. Now that's pretty hard to quantify in Australia. It's sort of just, for us, it's been given, it's there, it's occurring, we just ignore it and move on. And that 2% comes from the American, I guess you say, infrastructure studies. So it's something we need to probably look into more. You know, what's actually coming into our system, because it can come from things like breaks in the line, leakages and stuff like that in the main line. It can also occur as free-falling water comes through into the hot water system, storage tanks, things like that. It's going to come in and create bubbles and so forth. So, you know, things can be mitigated around that, you know, by putting, say, the feed line at the bottom of tanks instead of having them splash down. So entrained air, or dissolved gases, I should say, can have a real impact in there as well, and they actually can cause quite a lot of damage on their own, and that's when turbulence is really evident. It creates that cavitation, and what you can see in and around the systems is we primarily see that mixed in with installation issues, things like not deburring copper pipe or tube. So Mark and I will talk a lot today around copper tube, but as new, or not new, but different metallic systems come into play, things like stainless steel, if we don't fix these issues, it's going to occur, and we're seeing that occur quite quickly already with alternative systems, so it's very important along that space. So, dissolved gases cause localised boiling and cavitation bubbles to form at these turbulence, and you can see that a lot in the bends there. You can see where that turbulence is happening. On the left, bottom left there, you can see around where there's deburring, copper pipe, and as well in that join up there. Something that we see a little bit within trained air is in the top left there. You can see that where one side of the tube is heavily corroded, but not on the other side. So that suggests to us that there's something around air being trapped in that system, which is really creating that ability for corrosion to occur, and that's the eating away of that oxidised layer that's formed there. So we often see this in trained air and dissolved gases really playing into effect where there's high velocity and low flow, high pressure, low velocity, so I should say, where those gases and that entrained air isn't getting pushed and flushed out of the system. So the recommended velocities in the guidelines by the International Copper Association in the Services Design Guide is really based around the current knowledge that we have with entrained air and dissolved gases. So what's the solution? What's a train and a hummingbird got to do with it? So when Japan's high-speed trains were initially created, they created loud sonic booms as they entered the tunnels, and the engineers really struggled with this noise regulation. So the lead designer, Eiji Nakazatsu, he observed how kingfishers would dive into water at high speeds, creating very little splash. And so what he did is he took that design from the avian breeds, and he implemented it into the Shinkansen, and that's how they ended up with that long elongated nose. And so what I'm sort of encouraging here is a discussion to come around about how do we look to other, mechanical, for instance, other installations that we can learn from. We see a lot of mechanical installations. They use a lot of balancing valves. They use a lot of air bleed valves. Now, these are designed, obviously, to reduce noise in the system, create efficiencies, but are they also creating opportunities for the design to remove these elements from the system and become, I guess you'd say, because we don't see corrosion happen in the mechanical services, if at all, but definitely not on the scale that we can see happen in the hydraulics. So I'd really like to start engaging in those conversations, really understand what people's thoughts are around how we remove air that does enter the system, because it can happen quite easily. Again, we see maintenance crews go in and change out pumps and valves. So when this air is introduced at that point, well, how does that air then get removed from the system? Look, I don't want to take up too much of Mark's time because I know he's got a lot to cover, and it's very important what Mark covers in what we deal with here. So without further ado, I'd like to thank you all for having me, and thank you, Mark, for inviting me.
Brilliant. All right. All right. Excellent. All right. So I was here last year doing the national, obviously. That was, what was it, May last year, I think it was. And you guys invited me back, so, that's not my problem. Okay, so I want to talk about 3 main points because we have basically 10 minutes. So I'm glad I had a coffee before because that's kind of giving me a bit of fuel. All right, so what we are going to talk about is stuff that I hope is going to help you. Now, I know in the past, engineers look at it and go, well, what do I do? The hospital's already built, it's already gone through DLP, and I'm getting all these problems and I can't fix it. Or you're in the middle of a build and you're kind of going, well, I can't do anything about influencing change. Well, I'm going to try and hopefully help you a little bit, maybe. It might sell you a bridge in London as well, but we'll see how we go. All right. So, review from last year. That's actually a hospital emergency in the States. They obviously had a couple of emergencies going on at the moment. Looks like they may have been associated with the Titanic. But that was actually a chilled loop that actually failed and managed to flood their department. So, at the moment, we have got a multitude of health projects, particularly in Queensland, but we've got them in New South Wales, in WA, and so on and so forth. I am deeply concerned about what's going on. I am a part, as I know there's other consultants here are, but we are investigating quite a few facilities that are experiencing severe corrosion issues. One that I'm working with is well over $1 million in replacement costs just for pipe work, and it's not that old. So how is this happening? Why is it seeming to be, I'll talk to some of the guys particularly, and they'll say, we don't understand. We've had copper in our hospital for like 40 years, never had a problem. Why is it all a problem now? And it's a fair quality. And often they say, it's water quality. That's what it is. It's water quality, And I'm going to suggest to you, maybe water quality may have a contributor to it, but let's delve a little bit deeper. So, we're investing a lot of money in our healthcare facilities. We're doing them. They look fantastic. Excellent. But we've also got something going on which hospital engineers have to deal with, and that is the long-term effects of what's going on. Now, you're probably looking at that picture and going, has he lost his mind? No, because I never had it. But that picture there, now, I realised something. Like when I was younger, many of you I'm sure here will relate to this, that time in your life where your voice began to change. Do you remember that time? Some of you going, I think so. I can remember it just a little bit. It's that time where you suddenly notice girls. I don't know what happens with ladies. I think ladies, when they go through that time in their teenage years, they notice guys and find them more irritating. Or that was just maybe my experience. Anyway, right at that time, it's like God's way of saying, hey, slow down, fella. Slow down. I'm going to give you acne. That's right. So you end up with acne. My acne was so bad that I got offered a job at Domino's as a pizza. That was a good joke, I thought. You can use that one if anyone wants it. All right, but what I'm going to suggest to you, the best way as we're dealing with acne, but to deal with copper pipe corrosion, is to try and prevent it right at the beginning. Now, I think Sarah mentioned some of the areas before, and she's quite right. If we can deal with some of these things right at the beginning, we may save ourselves a lot of pain down the track. So, how do we do that? Well, the idea is to try and get in the ears of the designers. Now, that's challenging. Someone like myself, we're now beginning to work with the early design phase. Facility managers are getting you involved at the beginning to influence some of the decisions that are being made. That seems to be what needs to happen. Rather than velocities, you'd kind of think when a building's built, velocities are calculated by hydraulic engineers, right? Yeah, that's what they normally do. Have you ever seen anyone go around and verify them? No, I haven't really seen it. I've never seen the numbers. And the problem is that, and we found this, we're involved in a major hospital commissioning. We actually went around, we did measurements. Guess what? 50%, sometimes 100% above the specification. That's a problem. You just heard from Brendan, who was talking about the importance of these issues. Things like air entrainment in particularly hot water systems. I was on a site just recently, and they've got air entrainment, like bleed valves. Really good, except they're turned off. They don't work well when they're turned off. At least that's my understanding anyway. So it's these kinds of things. Reviewing and making sure things are correct. Unfortunately, unless you're retiring soon and you're part of a new build, you can expect pits to start to pop out after about 6 to 8 years if things have not been done potentially properly. Simple as that. You think back and go, and if you're part of a newer facility, when do you start seeing the holes? And research is quite good. It's saying between 6 and 8 years. It was from a paper that was done by the West Australians. Way to go, West Australia. That was some good stuff. I've got all the references there if you want to see them. That funny looking picture that's over on the left is actually copper oxide being peeled off of the internals of a pipe under an electron microscope. That's what it actually looks like. So the problem is that if you peel off the oxide layer of the internals of your copper pipe, it will be exposed to corrosion and it will bore through, and there is nothing you can do about it. There's no magical chemical that will stop it. It can slow it, but it won't stop it. So, the second one, if we haven't been able to influence the design, if we've got these intrinsic problems, or we've been able to influence good practice, we then need to make sure it stays correct. And so the way we want to do that is via the M process. You see, I'm just getting all these acronyms through there, so you're going to remember this, right? You turn on the radio and go, my goodness, what was that? Monitoring, management, and maintenance. There you go. Very good. All right. So these are some of the things that we actually do to monitor and maintain. So we can verify the effectiveness of the filtration. Well, we put in filtration. That's lovely. I'm very happy for you. Does it work? I've got a facility, that one that I mentioned, that's got to spend a load of money on replacing pipework. It's got filtration in it. That's fantastic, except the particles are smaller than the filter is, and it goes straight through it. Not very effective filtration, right? Because nobody bothered to actually look at an analysis first. They didn't bother to do the homework. That's the problem. Anyway, I digress. So, avoiding stagnation, dead leg management. There are always going to be dead legs in a hospital. Everybody, it's always going to happen, right? They're always going to be there. But we've got to be able to manage them, so we need to know where they are. We just, as I said, we're part of a commissioning of a major facility. They actually created a full dead leg register, and they did a really good job of it. It was huge. Looked like the Bible. But there's now a process in place to flush those dead legs. They're also putting in multiple corrosion racks, so they can actually measure corrosion in various areas and all this kind of stuff. It's not ideal, not the best way to do it in all cases, but it's not a bad way to do it. So that's why I've mentioned measure active corrosion rates. Don't assume that it's okay just because you haven't got pinholes, because guess what? 6 to 8 years, suddenly it starts happening, and you go, I wish I'd listened to that weirdo that spoke at that IHEA conference. Not me, of course. All right. Inspect the internals of pipework. If you can do that, that's fantastic. Velocity measurement. That can be done using non-intrusive velometers. So it's well and truly doable. And entrained air measurements. We're just developing some technology to actually be able to measure entrained air in particularly hot water systems. So that's actually pretty cool. And as you can see, I enjoy it. All right. Lastly, I did have a slide up there that said, I have pits, what do I do? But apparently that I don't know. What do you do when you've got those things? Can you get rid of them? Is there a magical technology? Well, the answer is no. There isn't. But what you might well be able to do is to slow them down. You won't be able to stop them, but you might be able to slow them down. So that's where using velocity, trying to improve the incoming water quality to help to reduce that risk. Make sure you establish limits. Now, you can't do that, but what you do is you call good-looking consultants like us, right? And we can come in and help you to actually establish proper control parameters that help you to reduce your risk. So, 3 points. Early prevention. Get in the face of the people that are doing the design. You will save a lot of pain for yourself if you can. Talking to HIQ. We have a really good relationship with HIQ. We work with them. We're trying to do more with them. We're doing stuff with VHBA. We're doing stuff with Vic Health, with New South Wales Health as well. M management. Don't just leave it for luck. Make sure you've got a process to make sure things are good. And if you have problems, there's a way of reducing risk. And that's using some of these strategies. There's a hook about to come out and pull me off stage. So thank you for that. Thank you for your time today.